Hi, and welcome to mini lecture 2 for week 12 of the Quantum Universe for Educators. In this lecture, we're going to talk about quantum entanglement and the Einstein-Podolsky-Rosen paradox. Last time we introduced the description of two particle states, for example, two electrons produced by the collision of two photons, and we introduced the word entangled to describe such a state. So let's talk a little more in depth about what that means. The state is described by this particular ket. So this wave function describes the two possible outcomes that you can make when you measure this particular state. You will either measure electron 1 to be spin up and electron 2 to be spin down, and that's described by the first part of this wave function, or you will measure electron 1 to be spin down and electron 2 to be spin up. Okay. Now, before a measurement is made, then the two electrons are in a superposition of both of those possible states. They are both spin up, spin down, or spin down, spin up. The electrons are said to be entangled. And it's important to note that in this state, the electrons are not separate particles, right? They are described by a single state, and therefore they are considered to be a single quantum system, even as they're moving apart to greater and greater separations. Okay, so let's actually consider making the measurement of the spin, and let's suppose an observer at A encounters electron 1 and makes a measurement of it, the z component of electron 1's spin. And let's suppose electron A makes that measurement sometime before another observer at B makes a similar measurement of electron 2. Well, if electron A measures electron 1's spin to be up, we know immediately that electron 2's spin must be down, right? That's the only possible option. And that is what electron B must now measure. And in that case, the wave function collapses into this form: electron 1 spin up, electron 2 spin down. On the other hand, if A measures spin down for electron 1, then B must measure spin up. Electron 2 spin must be spin up, and the wave function collapses to this state here. So we end up with this intriguing result that the measurement of one electron absolutely determines the outcome of measuring the other electron instantaneously. So you measure the spin of electron 1 and you immediately know what the spin of electron 2 is. And the tricky thing is that beforehand, electron 2 could have been spin up or spin down. So in other words, it seems that quantum mechanics is saying that when you measure the spin of electron 1, you influence the state of electron 2. Okay, you immediately and instantaneously change what its state is from a superposition of two possibilities to either spin up or spin down, depending on what you've measured electron 1 to be. And this is true if you measure the z component of the spin. It's also true if you measure the x component of the spin or the y component of the spin as well. Now, these measurements could be miles, light years, or even megaparsecs apart. Okay, these two electrons could have been created and then traveling apart for years and years, or millions of years, and one electron could end up on Earth and the other electron can end up in the Andromeda galaxy. And if an observer measures the spin of electron 1 in the Andromeda galaxy, then it instantaneously changes the state of electron 2. It collapses its state into either spin up or spin down on Earth. So this influence of measurement is something that happens instantaneously, and it spans potentially the size of the universe. So Einstein was, maybe understandably, not particularly keen on this consequence of quantum mechanics. He called it spooky action at a distance. And together with his collaborators at Princeton, Podolsky and Rosen, he wrote a paper to try and show that this actually directly implies that quantum mechanics is not a complete description of reality. And his argument goes as follows. So they firstly assume that because nothing can travel faster than the speed of light, whatever's happening at A can't actually directly influence what's happening at B. There can't be any faster than light communication between 1 and 2. So in other words, electron 1 cannot communicate with electron 2. So if we measure the z component of spin at A, quantum mechanics says we know immediately what the z component at B is. if electron 1 cannot communicate with electron 2, then that information must have traveled with electron 2. So the information about the Z component of electron 2 at B must have traveled with electron 2. But the observer at A may not have decided to measure the Z component of spin. It may have decided to measure the X component of spin at A. And if it does that, as we've seen, we then instantly know what the X component of spin is at B. And again, since the electrons can't communicate with each other, that information must also have traveled with electron 2, since electron 2 cannot know what A is going to measure. And this is crucial because electron 2 does not know ahead of time what observer A is going to measure, whether it's going to measure the Z component or the X component of spin or the Y component of spin, then electron 2 must carry with it that information. Somehow that information exists about electron 2, both the X component, the Y component, and the Z component of spin. But that goes against what quantum mechanics says via the uncertainty principle. So the uncertainty principle says that the information about the X and Y and Z components of the spin of an electron does not exist simultaneously. So we seem to have a contradiction here. If the electrons cannot communicate with each other, then an electron must have definite information about all of its components of spin, but that violates the uncertainty principle. So the argument Einstein, Podolsky, and Rosen made is that that means quantum mechanics is incomplete. That quantum mechanics doesn't tell you what quantum mechanics limits the information you know about an electron, but that information does exist. Therefore, there must be some underlying theory that we haven't discovered yet, in which tells us what that extra information is. Now, the idea that electron 2 carries all the necessary information in some underlying theory that we haven't discovered yet is known as a local hidden variables possibility, or a local hidden variables theory. All right, there are these hidden variables, hidden quantities that quantum mechanics hasn't got at yet. And we need to discover this even more fundamental theory that accounts for these local hidden variables. So how could quantum mechanics get out of this paradox? Well, it says that the assumption that Einstein, Podolsky, and Rosen made, that the electrons cannot communicate with each other, is slightly wrong in some sense. So quantum mechanics says electron 2 doesn't carry that information. There are no local hidden variables. But it's not that they communicate with each other, it's that they are the same system. Electron 1 and electron 2, before you conduct a measurement on them, are just a very, very large system that span possibly millions of light years. Right? So you cannot view the two electrons as separate entities. They are one system and they are non-local, which means they are extended over a large region of space. So we can say making a measurement of electron 1 at A does instantaneously affect electron 2 at B. But, and this is crucial, no information actually travels instantaneously. Okay, this instantaneous influence does not violate the principle of relativity, which says that nothing can travel faster than the speed of light, that no information can travel faster than the speed of light. The way to think of it is this. If A makes that measurement of electron 1, then the observer at A knows immediately what the observer at B will measure ahead of time. But the observer at A cannot communicate that information to observer B faster than the speed of light. So in other words, observer B can never predict ahead of time what the outcome of the measurement of electron 2 will be. So to observer B, the measurement will still appear random. So the question is, how do we test these two possibilities? We have the Einstein-Rosen-Podolsky possibility that the two electrons are separate particles that don't communicate with each other and that they carry with them all their information about their physical properties, such as the X, Y, and Z components of their spin. Or we have the quantum mechanics possibility that electrons 1 and 2 are just one single system that you can't view as separate particles before you make a measurement, and that the measurement of electron A does instantaneously influence the properties of electron 2 at B. So how to distinguish local hidden variables theory from the non-local description of reality of quantum mechanics. That's where Bell's theorem comes in, which we'll talk about in the next lecture.